to make it. Looks like we've got a pretty good mix of folks that are both semantic arts and kind of external. I'm going to post a link here to Graph Research Labs in the chat for folks, but I'm sure, you know, you've got a little bit of introduction as well. So I will just go ahead and hand it off to you. I'm not sure with your screen share, can you see the hands raised if people have questions, or do you want me to call those out for you?
I can't see them at the moment, so yeah, if you could call them out. Can you actually see my screen?
No, it looks black currently. It looked like there was something and then it went away.
How about that?
No, I'm still not. I don't know if anybody else is.
I'm still seeing black.
Okay. I'll just do that again.
Now it's switched.
Teams, it really hates me. It's got a thing against me. Right, I'll just try that again.
Exceptionally challenged as of late. Okay, so we can see the presentation, but not in presentation mode.
Okay, so if I hit present, does
it just goes away.
Okay, well I'll take it out of present. Now it stopped sharing. Okay, let's try that again. So does it show up now?
Yes. Yep.
Okay. Cool. Okay, well, I'll kick off. Morning, everyone. I'm not sure what time it is over there. I guess everyone's around the world. It's early morning in New Zealand. I always like to joke we live in the future in New Zealand. It's because it's Friday morning. It's a strange place. So today I'm just going to present some work that I've been doing on the semantic data serving layer, and this is the data-centric architecture onion diagram or grapefruit diagram, and it's interesting because it has some elements of potential solutions for, I suppose, pieces of that puzzle. So I'll just go through that this morning, and we could do questions all through. People could just interrupt when they like, or do it at the end. Don't really mind. So just so a lot of you probably haven't met me, I'll just give you a really quick background. I've been a practicing information and enterprise architect for more than 20 years. I was in New Zealand the chief technologist for IBM New Zealand, which was an interesting role around innovation and university outreach and dealing with the sort of hardest projects. During my time at IBM, I created a whole set of intellectual property around information, and I'll come to that in a minute. But I'm also certified in multiple disciplines. My journey to semantics actually started before IBM. I used to work all through Europe on different contracts, and I worked for Nokia Corporate in Finland, which was a really fun time working in Finland. And that's when I was first exposed to RDF, shortly after it became standardized, or just before it became standardized, I think. And I thought at the time, gosh, that's a really interesting model, you know, just that resource-centric view and being able to represent things in an extremely fluid way, I thought was super interesting. But it really came to a head for me when I was back in New Zealand. This is about 2008, and I was working for New Zealand's largest company. This is Fonterra. It's responsible for, I think, about 20% of our merchandise exports. It's the largest exporter of dairy products in the world. And they had this very extensive transformation program, moving from reimagining how their whole processes and technology work, from collecting milk on the farm, taking it to a manufacturing plant, and then delivering it to the customer. And that led to a whole chain of things in my architectural world, looking at understanding what solution architectures and enterprise architecture were needed. But the client then asked, I need an information architecture, and I thought, that's cool. Okay, being IBM, we have a method for that, but we actually didn't. And that took me on this whole journey. I was actually, frankly, really surprised. Our industry talks about this. We talk about managing information. There was no formal, repeatable way or even standardized definition of what that means. And so that started me on the journey of building this intellectual property for IBM, and I quickly realized it needed to have semantics embedded in it. And so a lot of what I'm going to talk about today is why semantics is not there in the enterprise and what we're doing to try and help that. When we train architects, we often use the example of the Winchester House, which is in California. It's a completely crazy piece of engineering and architecture, and it shows what happens when you don't have a cohesive plan for anything. I don't know if anyone's seen this in the wood, so to speak, but it's completely nutty. You know, you can climb stairs, open a door, and sort of it's like it's parodied in The Simpsons, and you could fall out of a door 2 stories up, sort of thing, because there's nothing after there. I love this: 13 bathrooms and only 1 shower. So that's a classic example, and the reason we use that when we train architects is that's very common in enterprise IT. So my career spans 30 years, 20 years being actually as a practicing architect, and you come across this stuff all the time, and you still come across it today. And of course, in architecture land, we have a lot of artifacts and methods and tools to try and control that chaos, and it's kind of an art and a science, which makes it really interesting. And it's really about marshalling these resources for change. That's a nice way of sort of saying it. And we often use this metaphor of city planning. You know, you start at this higher planning level, move further down, or strategy, then planning, then delivery. What I've called out here in red are the things that, again, as an industry, we have not defined, and we don't really kind of know what's in them, and they just are sort of as read by practice. There's no formality behind them. There's no real structure in how we do them, and that really struck me in my career early on. Why have we not bothered to understand what those things actually mean? Because they're super crucial, and they're really crucial. I rapidly came to believe that the reason there's very high failure rates in technology industry is because we don't think about data. This is data from the Disciplined Agile Consortium. This is from the Chaos Project, which has been ongoing for a very long time now. They record sort of resolution outcomes for projects in technology, and they're still finding very high levels of, if you look at challenged and failed, basically very high levels of projects that are either in distress or don't deliver. So we're still seeing, I don't have more recent numbers in this, but we still see this. We still see high rates of change. And Agile itself, there was a very slight improvement in those numbers when Agile really took off. But this is from the SAFE. I don't know if anybody's seen this. Agile itself is becoming extremely complex. And Agile really helps at the margins in terms of transparency, but it really does not help fundamentally with delivery outcomes in the holistic sense of it. Yes, it might deliver this sprint, or it might deliver this part of a project, but it does do a lot of things like lay down enterprise debt that's not ever thought about. So this one is completely crazy. This is really kind of, there's a lot of criticisms of this just because it's so extremely complicated these days. So I think the message from enterprise IT is that there's still a lot of problems. And in the last sort of 4 or 5 years in my practice as an architect, what I've discovered is what I call the stuck enterprise. So organizations have really become stuck at this intersection between where their business needs to move and where their technology will let them move. Or conversely, they know they need to move, but they can't sort of get over this hump to do the move, to do the strategic changes they need to do, in large part because their technology holds them back. So they do know change is coming, they can't really decide what to do, or they have a sense of what to do, but they can't sort of marshal their resources to make that change. Sometimes they really don't know the art of the possible, that technology will help them with that change. And so they become stuck there. And fundamentally, they're worried about making the wrong choice, and they're kind of held hostage by a lot of legacy. So I've sort of categorized that into 2 sort of areas. They've often got integration debt. So they just very, very, like I've even worked with companies with integration middleware that's dates from 2009, and they just don't want to touch anything because if they're scared if they touch it, it will fall over. But fundamentally, they're also faced with this concept of meaning debt, that they on one level understand that if they have to go and try and extract all of this data, extract their customer records, try and put them in new systems, try and rewire everything together, that they're likely to lose data. And they don't always think about it in terms of meaning, but they do understand that there's something going on with their data that's really problematic and highly, highly dangerous. So that there's actually lots of sources of debt, and I know various members of this group have talked about this in the past. But typically these are thought of from an application-centric point of view. You know, you've got these data silos. Some organisations have applications that are 40 years old, especially in banking, and they don't want to upset the apple cart by doing anything to those systems. Then they induce analytics debt because they're extracting data from source systems that are highly problematic, putting them in these analytics data silos. There's a lot of debt in code. Anyone that's ever worked on a code base knows that this happens very quickly. There's a lot of debt in these APIs, and this is where I'm going to come to in a minute. This is a really huge thing now that sort of crept up on us unawares. But there's also this sort of thing around culture and economics that is holding things back. And we often don't think about the economics in tech, but effectively this is an ecosystem with a massive inertia to change. It's what we know is what we do, and we're not going to change that. And we want to leverage that to do the next thing. But really that repeats the mistakes of the past in this application-centric world. So I mentioned APIs, and why do we really care about those? We care because they're incredibly pervasive in business IT and enterprise IT. They're pervasive because they do solve real problems. They're very easy to integrate, to use for integration. There's this massive ecosystem support now. We've spent the better part of nearly 15 years building these things. There's a lot of good standards like the Open API initiative, a lot of tool chains, incredibly extensive education of developers and uptake. So from the point of view of the culture and economics, you really win with APIs. And that they enable this massive uptick in mobile and web, which really came when the App Store was released quite a few years ago now. But they are incredibly problematic, and this is mostly hidden from most people, I think, including people in the industry. There's no inherent meaning in an API. It's really just JSON or YAML, and that leads to integration and meaning debt. They do create an enormous amount of data and metadata, which becomes problematic. It's a positive, but it's a negative. There's this massive weight of cultural change, economic resistance to change. But the most fundamental problem is that it turns out that there's a huge tool chain that's been built on these things, but the tool chain is almost entirely devoted to managing business logic or API logic and not managing data from an API's point of view. And that's, I'll talk to that in a sec, but what I find really interesting when I look at this is that you can almost run this, I mean, it's a terrible little drawing, but you can run almost a vertical slice through the data-centric architecture. So you have access to the endpoints, you've got things like security, access and logging, you've got the underlying data models if you want to sort of talk about it in the API sense. So the interesting thing is these represent a slice through the data-centric architecture. But as I mentioned, the API logic tools exist, but the data tools don't. And actually Gartner, the analyst firm, called this out in 2019. And there's a report you can log into or join to find called the Data Integration Hub. And it's a really interesting report. So they raised issues with this approach. Effectively what you get is spaghetti. So you get these things, even though you've got logic sitting in the middle, specific platforms designed to mediate between the outside world and the inside world, and serve logic and data. These things are causing problems and actually really serious problems. So typically what it results in is spaghetti wiring. And we're supposed to, as an industry, have gone away from that with integration tools. And you can actually have serious problems where very high workloads, you release a new app, oh great, you know, we've got a lot of customer uptake, and all of a sudden one of these core back-end systems, you're finding really high workloads because these things are talking directly through. And 3/4 of all API transactions are for just data requests. So very basic thing to be doing, but you can overload, especially older systems, you can actually overload these things and tip them over. or at the very least, you're going to require upgrades in the back end in these core legacy systems to start serving that data. You find other problems, like people just dump the data models directly into the APIs, so there's no modeling going on. You can often find trouble keeping these things running 24/7. And as I mentioned, that's spaghetti. So this is actually a really serious problem. And so Gartner called that out in 2019. And until we started building this, I'm not aware of another organization that's built a product to deal with this issue. Now, you might think that Semantics would come to the rescue. And I think the data-centric architecture manifesto is a really important step change in trying to get the enterprise IT world to think differently about this. But there's been, you've probably all seen this, there's been a really huge problem getting semantics into enterprises. Take up is really slow. There's a very scarce number of skills. Fundamentally, it's hard to program against. There's been attempts made to work between the API world and semantics, things like this, Basilar, linked data templates, various things like that. They're all really difficult to use, and they don't fundamentally fit between tool chains and semantic tool chains, traditional tool chains, semantic tool chains. So they're hard to program. There's actually very limited interaction between these ecosystems. It's mostly sort of looking over the fence and, okay, well, that stuff, yeah, knowledge graphs, the traditional world now knows about knowledge graphs, and uptake is fast, but uptake of semantics is still really, really slow. The semantic world typically doesn't really kind of interact that much with the traditional IT world, in my view. Fundamentally, I think it's caused because there's this impedance mismatch issue. But overwhelmingly, we use object orientation in traditional development. And that's what the industry has sort of glommed around. These OO languages, they don't really directly translate into ontologies. So you get this, what I call a downsampling issue, where you have a high fidelity semantics in the semantic world, and it becomes downsampled and reduced when it works in the OO world. So ultimately, to try and solve these problems that Gartner's called out, it's very difficult to make this tech stack, semantic tech stack, play in that API economy, at least if you wanted to think about it as a drop-in replacement. So having seen this issue writ large in the industry, I started Graph Research Labs about 18 months ago, and the mission is really embedding semantics into enterprise computing. Since 2008, I've been such a strong proponent of using semantics to address these issues. So it's really to try thinking about that issue that Gartner raised. It's trying to think about how we could solve that API data management issue, not solving the API logic. That's been solved comprehensively. We don't need to solve that, but that data management part of it. And creating solutions so that business computing challenges that have got really hard data problems can actually get some sort of solution, and really help semantics to flourish in that world. But without requiring, hopefully, practitioners to actually know or understand semantics. And that is really getting to that ecosystem issue. So back to the API issue. So one of our key goals was to try and deal with that API data management issue. And the concept is to centralize it into this semantic data serving layer. And that kind of looks roughly like this. I'll come to that in a minute. So there's some complicated things going on there. But what that really means is that you author the meaning of enterprise data in one location only. You generate everything else you need to integrate and then serve that data. And that's really, really crucial. So APIs serve the data. Nobody's exposed to Sparkle. People seem to be resistant to learning it. The schema required for integration, and then the connectors that use the integration schema for event-based integration, all of that's defined. So you have mechanisms to create APIs, to create integration at an event level, and also to create integration at a bulk data level. But the core concept is that everything's driven by declarative generators. And so if I'm old enough to remember 4GL languages, we used to sort of believe in doing declarative generation. The industry walked away from it many years ago, but I think its time has come again. So our goal is to build out everything is run off these declarative generators. So everything I mentioned, all of those ways of integrating and serving data, they all come out of this declarative generation world. And the source of the declarations are actually annotated ontologies. So what does that actually mean? So we have a set of layered ontologies, and I'll show what that looks like in a sec. So the semantics of the enterprise data are all defined up front. And typically you do that for either really for sort of vertical business problems. So things like open banking, there's defined standards in different geographies for that. For example, that's a good example. Accounting standards, there's all sorts of standards like that that are actually very structured. Well, they're relatively well structured. They're not semantic standards, but they have a good degree of structure. So you can build those out in an ontology model. You can also, at the same time, author the API definitions inside the ontology. And so you split your ontology into these axioms that the generators work off, and then the semantics of the data that are linked to those axioms. But what's really different in here is that the generators work off annotations against the ontology. So we have a separate annotation model, and we marry that up to the ontology, and the generators say, look into the ontology at runtime, and where they find appropriate annotations, that's what they use to build their artifacts. The ontologies themselves are authored to be pluggable, and they have very well-defined boundaries. I'll show what that looks like in a minute. So that effectively, for different vertical problems, they can plug into each other. But the really interesting thing that we're doing here is that we're actually going to allow end users. So I've said we've standardized the model, but we're actually going to allow publish these as an API, so that the end user can read and write against that API. They can pull down the YAML. They can effectively at their end generate code, which is an incredibly common use case with API technology. The semantics are invisible to them. They don't know under the covers that it's actually a sophisticated system running a triple store with ontologies with these generators. And we allow them to do controlled customization. So that means they can rename things, and we preserve all of the mappings between what the user does and what the ontology says. So they can change labels, they can change the name of things, they can turn things on and off. So if they don't want this endpoint, or if they want to reauthor a piece of a model, for example, we allow them to do that. And we either just reconfigure the generators, or if they change a model, this is quite a common use case as well. Okay, so you say this is what an account looks like. Well, we have these extra things in an account, these 5 extra fields. Okay, well, we let them add that. And we turn that into just an ontology import fragment, and then regenerate from that. So you have a very clearly defined structure and semantics of the enterprise data, and the user can do things around the margins on that. The system has to be triple story agnostic as well. At the moment, we prefer Neptune or similar things. We use other triple stores internally for testing, and then RDFox for ultimate performance for in-memory data serving. And then automation everywhere. So we run CI/CD on the code and the ontologies. So when they get checked into our repositories, there's various pipelines that run and do all the kinds of modern tooling things that you do to analyze code dependencies, security issues, and the ontologies. We also run CI/CD on those as well to make sure that they are structurally correct before they get committed. So what does that look like? So there's sort of 4 chunks to, if you imagine parachuting this into an enterprise. So the enterprise sees this top layer, which is they've got a browser or they've got an app, and they've got microservices that interact with an API. But that's really all they kind of see. They potentially see the management interface, which is this tool here. At the back end, they have various systems. They've got, for example, a mainframe. They have some integration middleware, which will typically be something like Kafka. And Kafka has a schema registering. They'll have bulk data that they need to do things with. And so their world is, okay, we've got these interactions at the front and we've got this data at the back. And really what we want to do is abstract over, we might have 50 of these things. We might have a credit card system we really hate, we want to get rid of it. But there's 50 applications wired to our credit card system. So how do we get rid of it? So we don't deal with the business logic, we deal with the data. The data is actually the hardest problem, I think. So we abstract all of the data into this layer here. And then in the case of banking, for example, we would use the, there's a set of standards in banking for semantic, they call it a semantic data model. It's not semantic in our terms, but it's, we took that and we upgraded that into ontologies. So in that case, there's well-defined APIs for accessing credit card data. So we would abstract that in this layer inside this database here. And then over time, it uses they have their logic processing already. We abstract the data. Over time, they can start to turn off the connections to this back end, and then they can swap out their legacy credit card system, for example. So this is an example of what that, and then in our world, this is our whole development tool chain and DevOps chain in there. The core pieces of this really are the system that understands your ontology. It brings the ontology on board. It runs different generators for different purposes. So the core generator will generate an API, and it will generate a container, an API container up there. And then the browser and the microservices can connect to that. It also generates a query manager, which is the piece of logic that's responsible for mediating between the OO world, the API world, and the graph world. And that's the interaction point into the graph databases. And then there's all sorts of things that you can add around the margins, like things like search. You know, and if you're using RDFox, it's got great search capability. If you're using Neptune, you know, you tie into the Elasticsearch, for example. But really, the bulk of it is actually mechanisms to do that. And then it will also generate. It takes the ontology and in parallel with this component, the registry generator, it'll go and generate schema registry entries. So it'll prime that and generate topics. It'll prime the integration middleware with definitions and say, this is the data that we need to flow into our system. And then in the back end, the data stewards and integration specialists who know their data are responsible for them for example, striping data through CDC and putting it into a topic. And we pick that up through this topic connector, which is married up to that registry entry. And a similar thing happens if we need to federate bulk data. So what does that kind of look like in practice? So the declarative generators, the two core ones are generating a YAML definition. This turns out to be massively harder than we thought originally. It's extremely complicated to turn an ontology into OpenAPI. Only very recently did OpenAPI as a standard, when it moved to version 3, did it actually fully support the ability to have what we call loosely termed sort of multi-homed properties. So you can have a class with two axioms that the predicate is the same and the object is different. That's that was historically impossible to represent in OpenAPI, but you can do it now. So we generate these YAML definitions, and there's some really interesting things that we do there. So, for example, taxonomies, which are crucially important. We're working on a product at the moment for climate disclosure. And if you have to build a climate disclosure to report your emissions in conformance with the Task Force for Climate-Related Financial Disclosure, this is becoming a standard around the world now. There's a lot of taxonomies in that thing. And so you need to be able to represent a taxonomy in an API. So we take loose hierarchies and complex cross-linked hierarchies and turn them into enums and arrays, and then they get attached to endpoints. And then, as I mentioned, these multi-valued or multi-homed axioms generating inline YAML. So that was actually remarkably difficult to do. And then generating integration schema. And so the most common one is this Apache Avro, which is really sort of a JSON-like structure. And then we generate those so that all of the schema in the API, and you end up with multiple schema in an API, they actually generate unitary or subsetted schema inside Avro for that integration level. So from an ontology point of view, just as the upper ontology, I really like just because it's got a great combination of the practical and ontologies, and it's tuned for business. So we use just as our upper ontology. We have a business ontology that imports that. So this business ontology adds additional concepts that are not in just. So it's kind of our enterprise ontology. And so it's got all of the core reusable constructs that we need to have in an ontology that we use to plug different models in. And it's got a whole lot of things that, for example, I've added from practices in enterprise architect. So definition of a business model, that's in there. Enterprise value, which is a more recent kind of construct. That's been put into there because it's required for the climate disclosure ontology. Then we import this annotation model, which our generators use, and so everything gets to be annotated against that model. And you can almost imagine that as an orthogonal ontology married up at various touch points with the business ontology. It's almost like you're kind of looking across dimensions. It's like a multi-dimensional ontology. And then there's these specific ontologies that are designed for specific use cases or applications. So we have a banking one. I can put that in. There's one for recording business events. We're working on this climate disclosure at the moment, which I'll cover in a bit. That's actually turned out to be the hardest ontology I've ever authored, interestingly enough. There's an insurance one, which is quite comprehensive. Prov as an import. We have a generic compliance ontology, which this extends, and there's one for open banking, which has really morphed more into Customer 360. So these are actually relatively complex. So this is the insurance ontology, and this is built to really manage submissions for policies. It's quite interesting. There's a lot of high level of reuse of a lot of core constructs and GIST, and then there's a lot of additions to it. But that was quite an interesting one doing that. And the intent with that one is ultimately we'll use that to generate downstream analytics for customers as well. But the one that we're really honing in on at the moment is climate disclosure. So this may not have hit the US much. I know that the SEC is looking at doing this now. They're looking at mandating companies above a certain scale have to report their emissions. And so the global standard is, as I mentioned, this TCFD, and it says that you need to be able to say what you're doing as a business to respond to climate change. And a big part of that is reporting your upstream, internal, and downstream emissions, the scope 1, 2, and 3. And it turns out that's a really hard, difficult thing to do. It's hard because it's quite complicated to do the work to actually understand that in the first place, but then to report it. The companies that have started doing this typically use systems where they just generate PDFs and then they kind of throw them over the fence to a regulator or to an audit firm. And that's really, we live in 2023, it doesn't really cut it. So it has to be turned into a model, and we're building an API on top of that model. It needs to be a computational model like an ontology, because it turns out that there's so many linkages between this data. It's a bit like supply chain. It's really, you can't really analyze it without a graph under the covers. So, for example, use case I heard the other day, I was talking to an entity and they have started to build out their reporting, and they said, well, we are really concerned because we're part of this city structure. We're a regional council and there's a city council. But we actually think we might be double counting their emissions because we share some infrastructure, and we can't tell because traditionally we just write this stuff down and put it in a PDF, and how can you audit that correctly? So that's one issue, but another is greenwashing is a really serious issue. And so being able to understand the provenance of the data and link up data across different entities for the regulator, it turns out to be a really, really hard problem to solve. So we're building that out. We're also building out a vertical app, which looks like this, that lets you build these disclosures. So the whole thing is driven off the ontology under the covers, and it marries up to the API that we're authoring on top of that model. We also have a generic horizontal product, which is a data serving layer. So this is a mocked up client. And this is the tool that allows you to, for example, if you're working in banking, load the Semantic banking definitions and start generating APIs for them. So this one here, this is actually the mapping for credit card, and you can see there it's got everything you need in an API: request response, got the parameters, it's got the schema. You can go through and you can edit the schema if you want. You've got all the ability to define, for example, high availability data stores, where your schema registry is, where your integration is, and then just deploy the whole thing. And that will go up and generate effectively the yellow boxes in there. And then it's ready to start integrating enterprise data and serving that credit card data. So I suppose in summary, what we're building, we're trying to solve this API integration data issue, but with semantics. This horizontal data serving layer product, that's the core of everything we're building. It's the core technology that we have. It's this middle layer that you sit between your traditional back end and your front end, aggregate your data into that middle tier, and serve it by these well-defined APIs, but they're all bound ultimately to an ontology. And the ontologies themselves are pluggable. So if you started with that banking, and for example, you just wanted to turn on credit card, you could also turn on provenance, and you could also turn on open banking. And they have quite well-defined boundaries in the business ontology. That's all of the things that are shared live in that ontology space. And so they can interoperate at a data level. So once you turn on provenance, it'll interoperate with whatever you've got already. If you turned on that open banking customer 360, the boundary is obviously customer and account and transaction, which are generic business constructs. So it just works in that sense. The other interesting use case that we came across was once you set the system up and you start serving data, especially large organizations are moving to event-driven data sourcing. But we're propagating the meaning of those schema, we're propagating the meaning of data into those event streams. And so this really interesting use case would be that you actually subscribe other parts of your tech stack to that event stream. So you might want to consume, for example, the definition of a customer that we've already put into the schema registry. And so you could have all of this analytics stack downstream from our platform consuming the same data. And so it's kind of data governance by the back door. You actually have the same meaning for everything in the organization. And since you're already streaming data in through those events into our platform to serve through those APIs, you might as well consume it in your analytics so that you have a consistent meaning. So that's the sort of the horizontal nature of what we're building to semantically serve data for APIs. But as I say, we're also building these vertical applications for the really hard data problems like climate disclosure. And the goal here is, as you see, provenance and being able to handle those really complicated use cases like different types of over and under reporting and greenwashing, and then electronically provide this to regulators to really sort of simplify the whole ecosystem and reduce the burden for organizations to start doing this. So, conscious I've been talking for a long time, so I'll just open up for questions if anybody has any questions.
Yep, Mr. Sullivan, hand up.
Yes, I'm surprised you didn't use Shackle to bridge that gap between the object-oriented world and the semantic world. It seems to me that if you're generating REST endpoints and other kinds of APIs, building them on top of something that's a closed world like Shackle would be much easier.
Yeah, there was. It isn't. I had done some previous work doing that, and we encountered some some kind of interesting difficulties. It's not so much at that point. It's the sort of well, there's aspects of that are difficult, but the internals to our platform is all the code is written in Java, so the internals of the code interacting with the ontology still isn't solved by something like Shackle. And you still need open world semantics internally anyway. So for example, if we plug something in to what existing ontology, you still need to have the ability to have open world semantics internally.
Oh, I agree.
So,
You need both, but in terms of, like a business object, can be represented very nicely as a shape, and bingo, you got your APIs, everything. At least for the, for singletons, you got quite a bit of it handled.
our sort of design goal was to support really all of the Open API v3 spec, and from analysing it, we felt that the easiest way of doing it was actually to use a mapping, effectively a mapping translation between ontologies and the Open API v3 spec. And so we have a sort of a tuple map that defines how one moves to the other, and it's the same tuple map actually that's used for federated data at the back end as well, and ultimately the same tuple map that's used for the generating the Avro schema. So yeah, you could go down that route. I've done it before a few years ago with shapes, and encountered some fairly sort of complex issues around that impedance mismatch that really sort of put me off going down that pathway. Doesn't preclude us using shapes in the future though, for some things. Any other questions? Who's got
Right,
the
Sean.
Yeah.
Thanks so much for your presentation. I really appreciated it. I was actually wondering, you made a bullet point about how coding against RDF is hard. Could you talk a little bit more about that?
Yeah, I guess it's not hard if you use Python, because there's some pretty good tools in the Python world, but it's hard if you want strong typing at the end. And we used some open source tools early on that were Python based, and they kind of caused a lot of problems. Which I won't go into the tedious internals of the issues that they caused. They cause issues if you wanted to kind of generate really authentic representations of the ontology. So this impedance mismatch issue turns out to be, it's quite a fundamental thing. In languages, strongly typed OO languages, if you're trying to represent multi-valued properties within one class, that's really difficult to do in traditional OO. It's not really designed for that. So our core technology that we build in is Java internally. That's as much a sort of an economic issue and access to skills as anything else. So, yes, you can do a lot of coding against RDF, but for example, Jenna, if you use some of the object libraries in Jenna, it doesn't really deal with the impedance issue, impedance mismatch issue. There's a lot of bugs in Jenna. If you use RDF for J, that's actually pretty good. But then you're actually really writing. If you go down that track, you're actually writing a lot of Java, and the point of this is not really to write Java and embed a whole Java ecosystem into an organization. The point of it is to embed an API layer that's effectively transparent to the organization. So that example of banking, you see, for example, open banking, all you ever see is an API definition that the industry agrees on already. And under the covers, the data is highly interlinked, very, very rich, and can be reused for other purposes, and has provenance attached to it, which if you did it in a traditional way would be very, very complicated to do. So that's kind of the design goal. So really, to be able to represent that API, we chose this tech stack. If you live in the Open API ecosystem and you look at the different generators, there's a lot of different generators in different languages, but they don't all support actually the same superset or subset of the specification. And so there's this very complicated dance between availability of skills, ultimate design goals of the platform and generating those compliant APIs. The open API generators, languages, and what they support, and so it's quite a hard thing to sort of to mediate out, and that took us a while to go through that whole decision tree and do some experimentation to work out which was the appropriate language really to build against. Because then, of course, you've got to work out if you choose a language that has really good generator support, front-end generator, API generator, not ontology to that generator, then you have to marry it up with available technologies in the semantic world. So what can I code against? So it's kind of multiple layers, if you will.
Thanks for that. That was great.
Yeah, it's a kind of quite a fundamental thing that we dealt with early on, and it's a really, really difficult question to resolve. quite a large decision tree at the end of the day to work that one out. Quite a lot of pain in coding.
Anybody else? Chris? Oh, and you're muted.
You're on mute there, Chris.
Can you hear me?
Yep.
Yes.
Great. So I think you did touch on this. Thanks for a very detailed explanation. And I think you did touch on this point, but I wonder if you can expand a bit on it, which is why you went down the route of APIs rather than, if you like, a generic Sparkle API, which might have allowed you to use multiple programming languages to access the information. Can you say a bit more about that, perhaps?
Yes, the reason that we generate APIs is they're the primary construct for interacting with the platform, and the reason for that it goes back to these issues in this report. So, as I said, I've lived, been an architect for a long time now, lived through the journey from SOA into REST. And your REST APIs have enormous traction in the industry, and it's not just people love to build against them. The app ecosystem, the app world came along. Organizations just have built so many apps and keep adding to them, hundreds of apps in most organizations, large organizations. And REST is the de facto standard for doing that, and that's not going away. And if you treat the enterprise IT as an ecosystem and you look at it like that, and from a cultural and economic point of view, you kind of have to work and you have to play in that world. And so the design goal was that we could build a semantic platform that you could literally drop in and nobody would know. So you just interact with a REST API. That's all you. If you're a developer,
but REST and Sparkle aren't incompatible. You could have had a REST API to Sparkle.
That's right. And so, but the issue with that is that when you try and do declarative generation from the ontology, the tech stack between the REST endpoint and the ontology and actually the data is quite a different tech stack to do that. And so, yeah, we could have done it that way, but there's a few things that you can't do in terms of Open API v3 support. And we wanted to support the maximum amount of that spec as possible. We also wanted to use some open source tooling, for example, the various generators. So there's the two biggies in the world are the Open API CodeGen and the Swagger CodeGen, and they're very large projects on GitHub. They have enormous rates of contribution. They're evolving all the time. So they're kind of like the de facto standard that if you wanted to generate a v3 compliant API, you really need to use those two code bases, one of those two, because you're on the leading edge of support for the standard. So as the Swagger, they used to call it Swagger spec, as that evolves, you support it. And so I talked about that dependency.
Yeah, everybody.
So you work backwards from that. Yeah. So if you work back from that, needing to support as much of that as possible, you end up not using the tool chain that you talked about because you don't get enough support at that level. So we actually looked at we did a survey of everything in the market all of the tools including the linked open data templating stuff, which is really Sparkle. It's a layer on top of Sparkle, and for those sort of reasons, we didn't go down that route. Also because we wanted to concurrently generate the back-end integration as well. And so, when you want to do things like propagate schema into this, you need to support Avro, because that's really the de facto standard as well. And so you can kind of get two for the price of one. So if you go and generate these up here, so part of the YAML's v3 spec, it's broken into these sections, and a big part of it is the schema, the component data models that are manifest through the API endpoints. And so when we generate all of that, we can peel out the pieces that correspond to, here's an endpoint that says I'm going to request this data. And it turns out that when you that all flows directly into the ontology. So we have classes inside the schema metadata, just schema metadata class. We have classes that sit in there that are effectively containers for other data, or they have axioms that point to other data entities. And so you can have your core ontology, which is preserved across time and across different things you plug into it. And then the request and response schema are views on top of that core data. And so it's actually really nice, because then at the same time, if I generate the schema that correspond to the YAML, I can peel out the pieces in the request and the response of what's the underlying real meaning of the data, and generate those Avro schema at the same time. And it's kind of the same tech under the covers. So you kind of get two for the price of one, which you wouldn't be able to do with a Sparkle generator. Also, the other aspect to that, and why we do it is when you do need to allow a degree of customization in this. So you need to be able to say, like, if I'm an end user, which we see here, I might just say, well, to turn these things off. Then I might want to go and change some of the, in this schema here, I might say, we actually need to add 2 more fields. And so that has a massive impact in all the rest of your infrastructure. So effectively, you're allowing an on-the-fly data model change. It kind of isn't. So there's 3 classes of change that you induce in the model, which we deal with. And so if you follow the logic of what that means to the code and the platform, that's why we went partly the way that we did, because we can at runtime dynamically change the internals of the platform to respond if a user customizes in that front end there. So the user comes in, they log into this, and they change the meaning of some part of the data. It has to flow all the way down to here. It has to flow to there, to the federation. It has to flow into the graph database. And so we do, for some of those, 2 out of those 3 cases, we do dynamic rewriting of what the user has asked for, because it's all driven by annotations. And the annotation actually gives you more flexibility than the shackle does. So we can, for example, if there's a class, we have a set of annotations which mean that when it's manifested in an API, it looks like this. The ontology, its pref label is this. From an integration point of view, it might look like this. And if a user rewrites it, we just write another annotation against that class. And so the meaning of the data doesn't fundamentally change, but the way that it's consumed, the platform goes back, it sees there's a change in the annotation model, and it regenerates the things that are required. So the query manager regenerates the difference between, and this will regenerate the API, or that piece of the API. The query manager will pick that up as well from there. And the query manager will, in real time, do a dynamic rewrite. So if it sees something inbound from an API that says, customer used to be customer, but now it's plural. Okay, well, I still know what that means. And then I run the query against customer at the back end, for example. That's a simple, kind of a simple example, but so you actually get, and that was the other reason we didn't go down the shackle route, because it's kind of not needed, because you have this flexibility through this annotation model. So the annotation model actually, in a sense, from the point of view of at least 2 of these generators, defines closed world semantics on the data.
Doug Beeson, next hand up. Oh, you muted.
Yeah, thanks.
Mhm.
Yeah, this is super interesting. I just wanted to, you maybe were going down that path already, talking about the generators, but I wanted to ask you, is the output of these generators materialized? Is it stored on disk, or does it go into the semantic graph? Or does it just live in memory until you restart it and then you regenerate everything again?
Yeah. So there's two aspects to that. Typically, it does live in memory, and that's because the CI/CD pipeline here, it's deployed in the meaning of the data. So here's an ontology with a set of annotations, and then everything works off that. And so that's if you imagine at runtime, there's kind of build time and runtime. So build time is when it gets deployed, and so all of that's stood up and it's running. And now I can issue a query through a microservice, for example, to an API that's been generated. But now I go, oh, maybe I'm building out a new app, and I go, oh, I don't really like the way that looks. We don't use that language, even though that's the standard. We would like to use customers instead of custom. I'll use a really simple example. So the API manager logs into this schema manager, which is this app here, and they go, okay, I'm going to change some of these mappings. And we'll just change the word customer to customers. And so the platform, now we're in runtime world and not deploy time, the platform will go and record that change. In that case, it will materialize that change, it'll store it. So there's a it's not shown here, but there's a CI/CD pipeline internal to this yellow world for that customer. And so it will actually store that definition. And so it stores it as RDF. So because it should all be RDF. Love the RDF. So it stores that annotation as RDF. And really what it means is if the import tree, you've now got over the side, you've got a customer annotation model, and it's got obviously a well-defined injection point that says for this class, that annotation applies. And then it's, in that case, actually probably we'd just rewrite the API label. And so the generator reruns when it picks the change up, and then it modifies the API. Probably in that case, it would mean it would have to redeploy that endpoint at least. So the container gets modified, and then the query manager, because it's paired, each instance of that is paired to that, it'll pick that change up from customer to customers, and then it does. It's got a binding between the customers class in the container for the API. To the ontology, and then to
you
the
almost have
mappings as well.
you almost have build time, tweak time, and run time.
Tweak time can be at runtime, yeah. We only
time
sort of
can be at
differentiate between the two, yeah. But
Okay.
There's three classes of modification. And one of them is structural. The rest of them are kind of trivial. The rest of them are named. The others are naming, but the structural one will require creation of something a bit more. So if the customer goes, now I've changed it to customers, but I'm going to actually add two name value pairs because we record a bit of extra data. It's actually a similar mechanism. In that case, what we would do is we'd generate another stub of RDF, and we would deploy that. But that's actually slightly more sort of structural change, if you will.
Right.
But it's really kind of the same mechanism. Yeah.
Great. Thank you. This is excellent. That's what I wanted to hear.
Just another second. Michael Sullivan, you got a quick one?
Yeah, just besides REST and other APIs, do you anticipate supporting GraphQL in the future?
Yeah, I built a GraphQL endpoint in a previous organization. So we used Antler as the generator, which is really amazing technology. But you have to bound it. So we actually built apps that were working off a GraphQL UI against a graph. This was in, excuse me, 2018. And you can actually, you have to be extremely careful because, well, first of all, GraphQL doesn't have a great security model, but you can actually allow querying that is effectively like ahead of time, you don't know the cardinality of the query. And so you can have really serious performance problems if you're not careful. So you kind of have to do something to try and restrict what a customer is allowed to do. Because, if you look at an ontology like this, like that, hopefully you can see that that's an insurance contract. Look how joined, so you don't want to allow like a select star from insurance contract type query, in GraphQL, because it's an unbounded query effectively. Imagine trying to retrieve that. There's a 23, I think from memory, core classes that live off that. So, you can overwhelm the graph no matter how powerful it is if you're not careful. But we would probably do it. We've thought about that, and protobuf is another one that we might do. But probably what we would do is modify the annotation model, have another annotation model, because GraphQL is just to us an integration type, and there's a typology of integration technologies inside that model. And so we might then bound allowable queries in some way. I don't know what your experience if you've used GraphQL against graphs, if you've had that issue.
Great. Well, thank you very much for joining us here. Out of time. Yeah, we will get this recording posted. I'll make sure to send you a copy if that's valuable for you as well. But appreciate you taking the time to join us here. I guess in the past for you, but we will look forward to seeing everybody here next month.
Thanks so much, everyone.
Thanks, everybody.
Thank you very much.
Bye.
Cheers. Take